This video introduces perturbation methods, an important technique in applied mathematics. The idea of a perturbation method is to construct approximate yet analytic solutions to otherwise intractable problems. The way we do it is by identifying certain small parameters in the problem. We're going to illustrate the procedure of perturbation methods by revisiting our moving target problem. So I did the moving target problem video a bit earlier, but you don't need to watch that in order to understand what is going on here. So the video is self-contained. Here's the basic scenario. We have the launch point and the target at the given moment. The idea is to launch a projectile in order to intercept the moving target at a future position. So these numbers are given. R, that's the current target range. Theta is the direction of the target course. So you see T prime T, that's the target course, and OT, that's the line of sight. They form an angle, theta. U is the target speed, and V is the projectile speed. So given these, we are asked to find T, that's the hitting time, phi, that's the firing angle, R prime is the future range, and L is the lead distance. And these are the exact solution previously shown. We've shown that if the target is slower than the projectile, then there is a unique solution. This is how it works. First, we calculate the firing angle, phi. That's the inverse sine U over V times the sine of theta. Once phi is calculated, we then calculate T equals to R over V times the sine of theta over the sine of theta plus phi. T is known, and then R prime is just V times T, and L is just U times T. That's the exact solution. However, exact solution provides little insight if we wish to analyze the problem qualitatively. For example, how does T behave qualitatively when U is much smaller than V? The target is moving a lot slower compared to the projectile, as it's often the case in real life. The perturbation method, albeit is not exact, it provides much better insights into the qualitative nature of the problem. And we'll see how that works. Here's the perturbation solution. Step 0 is to establish an equation for T in a way that does not involve the intermediate variable phi. We can do that by using the law of cosine. In the law of cosine, we have OT prime squared equals to OT squared plus TT prime squared minus 2 times OT times OT prime times cos theta. Next, we're going to non-dimensionalize the equation, meaning transforming the equation so that every variable appears is dimensionless, that is, having no unit. This can help us reduce the number of constants in the equation, so the equation looks cleaner, and it also helps us identify small parameters. Here, I'm going to define these new symbols. T0 is R over V. That's just the stationary hitting time. And epsilon is U over V. Because here I assume U is much smaller than V, epsilon is a small parameter. And also the dimensionless time, capital T. Capital T equals to T over T0. And now I'm going to focus on solving capital T. So essentially, we're treating the stationary hitting time as the time unit in our problem. Now I'm going to divide the law of cosine equation by R squared on both sides. We use the fact that R equals to T0 times V. The left-hand side reduces to T squared, capital T squared. The right-hand side becomes epsilon squared, because we have a U squared divided by V squared, that's epsilon squared, times T squared, plus 1 minus 2 times epsilon times T times cosine of theta. So you see the last term, one of the R's cancels, and you use R equals to T0 times V to get the epsilon and capital T. This box equation for T is going to be our focus now. We notice something in the box equation, namely if epsilon equals 0, then the equation reduces to T squared equals 1, and that means T equals 1. This is hardly surprising because epsilon equals 0 corresponds to the stationary target scenario. And we call this the solution to the unperturbed problem. Then we're going to propose an ansatz, that's an educated guess for the solution, in the form of a power series of epsilon. It goes like this. T equals to 1 plus C1 times epsilon plus C2 times epsilon squared plus higher order terms of epsilon squared. The constant term is 1 because if I set epsilon equals 0, I should recover the unperturbed solution, namely 1. So here C1 and C2 are unknown coefficients that are independent of epsilon. Our goal here is to solve for these coefficients. What follows is fairly mechanical. You're just going to plug in the ansatz into the equation for t. Let's see how that works in detail. This line is nothing but the equation for t copied down. And then I plug in t squared. So how do we square this thing? Because we only care about terms up to the quadratic term of epsilon squared. We don't need to write down everything explicitly, because if you see any term that are of higher order, you can just throw that into the O epsilon squared. Think of O epsilon squared as a garbage collector. So first, let's square 1. You have 1. Squaring C1 times epsilon gives C1 squared epsilon squared. Squaring the third term gives us C2 squared epsilon to the 4th. And that's a higher order term. So we don't write that. You can consider that being thrown into the garbage can. Then we move on to the cross terms. We have 2 times C1 epsilon, that's a linear term, so we keep it. And 2 times 1 times C2 epsilon squared, that's a quadratic term, and we keep it. And the cross term between C1 epsilon and C2 epsilon squared is a cubic, so we put that in a garbage container. So this simplifies as t squared up to the quadratic term of epsilon. Then we focus on the second term, 2 epsilon t cos theta. Here, because we already have an epsilon, we just need to keep up to linear terms in the ansatz. So now let's expand everything and then collect terms. Now let's collect the powers of epsilon. One, that's the constant. This is the combined linear term, and this is a combined quadratic term. This line right here is the final simplified version. Now, because of the equation holds, both of these coefficients must vanish. So we set that up and get equations for C1 and C2. So now C1 is solved. So we can substitute C1 into the second equation for C2, and we'll read cos squared plus 2C2 minus 1 minus 2 cos squared theta equals 0. So you just rearrange that and you get C2 equals to cos square of theta plus 1 over 2. And we have the expression for capital T. After finding the dimensionless time, we can then redimensionalize to get the physical time. Now let's introduce delta T equals to T minus T0. That's the hitting time difference between the case where the target is moving and the case where the target is stationary. If we're only keeping the first order contribution in the perturbation solution, we have delta T over T0 approximately equals to minus U cos theta over V. And this equation is much easier to interpret. And now let's move on to the interpretation of the box formula. If theta less than half pi, that means the target is moving closer to the launch point. So in that case, delta T is less than 0 because cosine is positive. This is consistent with our intuition. If theta is equal to half pi, that means the target is moving orthogonal to the line of sight. Delta T is approximately 0. And last but not least, if theta is greater than half pi, that means the target is moving away from the launch point, and delta T will be positive. And also, U cosine of theta has an interpretation as well. Because if we look at the diagram, here we have OT, the line of sight, and U, that's the velocity of the target. u times cosine theta is exactly the component of the velocity along the line of sight, which I denote as u parallel. So now we can appreciate the value of perturbation solutions. Usually they provide much better insight into the qualitative behavior of the problem. So lastly, in this part of the video, we will verify that the perturbation solution we obtained earlier is indeed an approximation of the exact solution. Here, because of the equation for t is a quadratic equation, we can obtain the exact solution via the quadratic formula given as such. Of course, we omit the negative root. And then I'm going to directly expand the right-hand side using a few well-known series expansions. The square root of 1 plus x equals to 1 plus half x plus higher order of x. And also 1 over 1 minus x equals 1 plus x plus higher order of x. So t, the exact solution, can be expanded as such, where I use the series expansion for the square root and the fraction. Now we just need to expand this out and collect terms. Same method as before. And this turns out to be exactly the same as the perturbation solution we obtained earlier. So here we are able to verify the perturbation solution via the exact formula. This is not the case, however, for most applications of perturbation method. And in fact, perturbation methods are especially powerful when an exact formula is not available. That's the end of today's video.